Okay, now we need to talk about what an integral means, okay? Because almost universally people come out of pre-calculus not understanding what an integral is, what it tells you, what it means, or how to interpret it. Okay, you get caught up in all the little details and you never see the big picture. The biggest picture for an integral, and I'm assuming you understand that the integral of a function is whatever is the definite integral of a function. The integral of a function over an interval is whatever is represented by the area under the curve on that interval. Now there are all kinds of little details you got to worry about. What if the curve goes below the axis, above the axis, and so forth. So my statement is a little bit imprecise, but it's easy to fix if you have that basic understanding. If this is a function, then the purple shading is the area under the curve. Okay? Whatever that area represents is what the definite integral means. We have the area under this curve between 0 and 10 seconds. And maybe I should be explicit about the 0 there. Okay, we got 0 seconds here, 10 seconds here. Now, if 10 meters per second is up here, then what's the area of this rectangle from here to here to here to here? Okay, and back. Okay, the area of this rectangle is bounded above by the green line next to the 10 meter per second. Okay, well, people were pretty quickly able to tell me, well, that's 10 meters per second, that's 10 seconds. When we multiply them, we get 100. And I think the answer I got in class actually included the unit. Okay, well, it's not just 100. It's 10 meters per second times 10 seconds. The area of this green bounded rectangle here, the big rectangle, is 10 meters per second multiplied by 10 seconds, which is 100 meters. Or rather, I'll say the area of this rectangle would represent 100 meters because it's a product of so many meters per second times so many seconds. If you multiply meters per second by seconds, the unit you end up with is meters. The interpretation is obvious. If this is velocity and this is time, then you're multiplying a velocity by a time. This is how far you would go if you moved at 10 meters per second for 10 seconds, and that is what's represented by this rectangle. Now, the purple shaded area is less than the area of this rectangle. So I can say that the purple area, which is indicated by this arrow and by this shading, is less than 10 meters per second times 10 seconds, or 100 meters. Okay, well, my next question is, okay, what do you think the area under that curve does represent? How many meters do you think that area does represent? And most people thought, well, the area under this curve, it's kind of irregular, so the region up here is kind of irregular, but if I cut this out and cut this region out, cut this rectangle into the two regions, the region below the curve and the region between the curve and the 10 meter per second velocity, that the area below would be a little bigger than the area above. So we kind of agreed, well, okay, looks like maybe that area should be 60 meters, okay? Because half of the 100 meters, of course, would be 50 meters. So it's a little more than half. Let's call it 60 meters. Okay, that's a reasonable estimate. Okay, well, what did you just estimate when you estimated the 60 meters? You estimated the area under this curve, which is what the integral would be. Okay, so your estimate of the integral is 60 meters. Okay, how did you get that estimate? Well, you compared it with the area of this rectangle. Now there's another way to estimate it. So what I ask people to do is, first of all, give me some quantity that this integral is definitely greater than. Okay? And somebody said, well, let's use 2 or 3 meters per second because this blue line here, for example, which I didn't draw in class, but this blue line is at the minimum value of this function. So if the minimum value is 2 or 3 meters, then the area under this blue line would be 2 or 3 meters multiplied by 10 seconds, or 20 or 30 meters. So we're pretty sure that the area here is greater than, let's say, 30 meters. We're pretty comfortable with that, even if, this is, even if 30 meters is a little higher than this minimum, it's still clear that most of this curve lies significantly above the 30 meter per second, or the 3 meter per second value, okay? Then I said, okay, well, what do you think the average value of V is? And this thing here is a question mark, but it really, I had to ask myself, wait a minute, what is that symbol I drew? Okay, that's a question mark. Is this the average velocity here? Okay? Or is the average velocity a little lower or a little higher? And what do you think the average velocity is? And people generally agree, well, it looks like about 5 meters per second. Okay? Well, if the average velocity was 5 meters per second, then multiplying the average velocity by the 10 seconds would give us 50 meters. Okay? Now that's a little different than the 60 meters people got by eyeballing this region versus this region. And you reconcile that by, well, should the two be equal? Okay, well, they should. If you multiply the average value of V, whatever that happens to be, by the 10 seconds, you should get the area under the curve. That's exactly what we mean by the average value. The average value multiplied by the interval, and by that I mean the interval on the horizontal axis over which we're integrating, is equal to the area, or that, of course, represents is whatever's represented by the integral. So the integral, or the area, is average value multiplied by the interval. Now, that's the very first thing anybody should understand about an integral. Now, that's just my opinion, but nobody would disagree too seriously with that. They would certainly agree that to understand what the integral is telling you, that's one of the key things you have to know. And it's one thing that nobody seems to know. You have a little section in your book that says calculate the average value and gives you a formula, and you use that formula, you calculate it, you get it on your paper, you get it right, but you never really understand what it meant, or you would still remember it, and nobody ever does. Okay, so let's key in on the idea that the integral is the average value multiplied by the interval, which means that the average value is what? Well, if the average value times the interval equals the area, or the integral, the average value is the area, or the integral, divided by the interval. So that's implicit in what I've written here. And you really, really need to understand those relationships. You need to immediately know, well, I can estimate the integral, and then I divide by the interval. That's going to give me the average value. Or I do the integral and divide. Now you can do that without understanding what anything means. That's why I think it's important to estimate this and understand the picture of what it means, okay? And somebody else said, and it was a very good observation, you just slice this thing up and you add up all the areas, okay? If you slice it up evenly and average all the areas of those slices, you get the average value. If you add up the area of all the slices and take the limit, of course, you get the integral. And all that goes together to confirm what we do here. And that's actually how you prove that the average value is what we mean by this. Now, actually, this is how we define average value. That's how you prove the average value really means what we would ordinarily think of as an average. Okay, bottom line, average value times the interval equals the area or the integral, okay? The average value is the integral divided by the length of the interval.